All right, guys, this is the lab-free tutorial video. This lab will use the force-stable online remote file. And this lab has two ways of completing it. You can use the GeoGebra software here that looks like this, or you could use the exploration physics. Now, if you have done this, you know that you can access several simulations. This one is basically the force stable. Basically, you will be using this. The only issue is that you need to input everything in newtons, which at the end of the day, that makes sense because you're doing forces, not masses. Now, at the beginning, you're just using two forces, so you will do this, and then you will change the angle as stated in the manual. All right? So let's take a look at what you need to do. Let's open this as well, just in case. You are going to be adding forces, and you're going to be looking at the resultant and the equilibrium force. If you have the force table, then it will probably be better and easier to look at the equilibrium. The resultant will also be easier to be observed. However, you can also observe it in the GeoGebra app. Now, as you can see here, the GeoGebra app, you can input things in terms of masses, but it doesn't give you the equilibrium. It gives you the result. So you may want to use both if you want, or you can just use either of these, GeoGebra or the forces table in exploration physics. Okay. So the data is given in the table. If we go here, you can take a look at the theory behind the lab. This is what you will use in an in-person lab. These are the masses that will hang, and these are the cables, and you will have a tension there due to this mass. You know, mass times gravity is a force, mass in kilograms, gravity in meters per second square. And here is the data. So you can use thing number one, that's okay. 300 grams, 125 grams, different angles. So let's suppose I use this in the exploration physics, all right? So 300 grams at 120. Now, 300 grams, we have to eventually do this. So we have to go to the calculator and convert that into newtons. So 300 grams divided by 1,000, that's a mass in kilograms, multiplied by 9.8, that's basically 2.9 newtons. So we leave it like that. And 120 will be here. All right. That's your force there, clearly 120. Here you have a graph. Here they give you the net force. That's going to be important for later. And then they give you that 125 grams at 195 degrees. So 125 divided by 1,000 multiplied by 9.8, that's 1.2. So here we go to 1.2 at 195 degrees. Okay, so the net force, the resultant, is 3.4 newtons, if that's the number of sig figs, at basically 140 degrees. 140 degrees around here. Now, 140 degrees, that's the direction of the resultant. If you want to find the equilibrium, that's when you use this. Now, the equilibrium has to be the same magnitude as this, but it needs to be at an opposite angle to the resultant force. If this is 140, I need to find an angle right here that is opposite to the 140 here. Now, 140 here means means exactly 50 degrees here. So I will create a force here of 3.2 at an angle of, so I want this to be 50, right? You want this to be you want this to be 50 degrees here. And that will make 50 here. So 360 minus 50, 310. So makes sense here. Make it like this, around there. And if I play this, uh, 50, 50. Let me see this. Let's stop this. We don't need this force. So 3.413 at 140 degrees. That will be 140 minus 90 is 50 degrees. So you want 50 degrees here on this side. 360 minus 310. It's weird. Okay, so I get net force of 0 after. So it's close. It might be because of the amount of force. So let's make it a bigger angle, maybe 313, and let's see. So what I'm doing right now is I'm looking at the equilibrium. For the equilibrium, that shouldn't move that much. And it should be like that. You see? So because of the uncertainty in the experiment, right? I'm playing with this a little bit. I'm seeing that the equilibrium is about 3.4 as expected, as the resultant force, at about 320 degrees. So this angle is 320 degrees here, right? So you will write that in your lab manual, in your results. Here, you have that should be the mass in grams, the force, so you have to do the conversions as I did. The equilibrium will be what I just found, so 3.4 newtons. Here, 3.4 newtons at the angle of 320 degrees. Now, the weight, how do you go from newtons to grams? So 3.4, you divide by 9.8, that's the mass in kilograms, multiply by 1,000, that's 347, basically, grams here, right? The resultant theoretical, you can just use the one given in the software. If you have done the math in class, you can show me the math. I'm not gonna ask you to do that because, again, this will require some trigonometry, okay? If you have questions about it, you can send me an email, all right? But basically, the question is asking you to find the resultant of these two forces, this force and this force, and obtain this value. So again, this can be treated as a theoretical value. If you want to show a calculation on paper, you can use the law of cosines. So 120 and this 195. So 195 minus 120 is 75 degrees. So the way you will do the theoretical value will be by using this. So the resultant will square will be 1.2 square plus 2.9 square minus 2 times 1.2 times 2.9 times the cosine of the angle in between, which is 75 degrees. In degrees, of course. So then that should give you the resultant theoretical. You just take the square root here, and then you calculate this and do. All right. So you can do that. You can do that. And then also you can graph this. You can just use this graph and then put it in the lab. That's important. That's part of your data. So let's see how you will do this in GeoGebra. So in GeoGebra, you have an advantage. You can put the masses in grams. So let's take a look. I'm doing this because I know some of you won't have the software available. So might as well show you how to do this using this as well. So 300 grams, 120. And then this is 300 grams. So 300 grams there. That's the mass, that's the theta value. And then this is 125, 195. So 195 degrees and 125 here. There. So yeah, look, at 140. Remember what we got in the previous one? So they give you the resultant and the angle there. So that's the reason why it was getting hard for us to do in acceleration physics to find the resultant. Because I put 3.4. It's actually close to 3.5. This is more accurate. They give you an extra significant figure that you need. All right? So the equilibrium, you cannot see the equilibrium here, but you have this protractor. So the equilibrium will be 3.47, and then the way you find the angle, and I can show you guys that in here, is by using a ruler. You can trace a line like this or linear there. And then it is, you see 320 there. All right. So this was more accurate than the previous one. All right. You have the angle and you have the value of the force in newtons. All right. Of course, you could maybe add it here with M3. So M3, 3.47, we said it was about, well, let's do the calculation again. So let's open the calculator. Oh, 347, right? So we could do 347. Oh, well, this doesn't have that. It doesn't go to 347. So let's put 350, an angle of 320. Oh, what am I doing? There. So there you can see the resultant there, right? I can erase this. There. So there you are. That's your resultant there. The equilibrium, sorry. The resultant was here. Okay. You can see why there is no R now in this for these free forces. Because R is 0. This is the equilibrium of the resultant that was here. All right? So you can do that. You can use this as well to complement what you did. So the next experiment is the same. All right? You just have to use different angles. But the idea is the same. Be careful with this lab. You're going to have to give it more time. You do want to do some graphs to help you with the calculations. But other than that, I don't think you will have major difficulties. The second part, you have to use 300 grams at 0 degrees, 400 grams at 90 degrees. So they make 90 degrees. And then you can find the equilibrium just like it did in GeoGebra or in exploration physics. Make a sketch. The sketch can be basically like this in a graph paper if you can. And then you have a few questions to answer here on the table and here. All right. So this lab will take you a bit more of time. If you do the trigonometry in class, you can apply it here. If you do not do the trigonometry in class, just use the software. All right. Don't give up on the lab. All right. I'm gonna be honest. This lab is probably easier and more useful to do it in person. You can actually see the masses and you can see the ring and the equilibrium forces. It's probably even more entertaining, but you can at least do something online. All right. So don't just give it a try. Do it. And again, I'm going to be available for any questions online at any point. Okay. So see you guys in the next tutorial. Have a good rest of your day.